Greetings, AP Chemistry students. Today we're going to be working a little bit more with acids and bases and pH and equilibrium. Also, linking in the assignment the answer key to Friday's assignment. Uh, so today we've got a few things to talk about. The first thing we're going to consider, as I've mentioned last week, that the kW of water is 1 times 10 to the minus 14th at 25 degrees Celsius. And on the AP exam, unless you're told otherwise, you should assume that the temperature is 25 degrees Celsius. But sometimes you may not be at 25 degrees Celsius. So, for instance, I have the kW for water at three different temperatures. And what you should notice is that as the temperature increases, the value of the equilibrium constant also increases. And keep in mind that we are talking about the reaction where liquid water makes H pluses plus hydroxides. And our equilibrium constant Kw equals the concentration of H plus times the concentration of hydroxides. So if the value of the equilibrium constant is increasing, that means the amount of H pluses and hydroxides are increasing, which means as the temperature goes up, our equilibrium position is shifting towards the right. So this means that at a higher temperature, this is favoring the products, meaning it's essentially that heat is like a reactant. As you put heat into it, it shifts it towards the product side, meaning that the dissociation of water is endothermic. And if you think about this from kind of a logical standpoint, essentially you're having to break a hydrogen oxygen bond, which is going to require an input of some energy. Of course, we're also omitting the fact that you're technically forming H3O plus, so it's a little more technical than that. But this is endothermic. The data here demonstrates that. So if this wanted us to know what is the pH at 50 degrees Celsius, well, if we set up an ice chart, the H plus and hydroxide concentrations both go up by X. So they're equal to some amount X at equilibrium. And so then we say 5.5 times 10 to the minus 14th equals X times X, or X squared. So our H plus concentration would equal the square root of 5.5 times 10 to the minus 14th, which is 2.3 times 10 to the minus 7th, which is our H plus concentration. So the pH would equal the negative log of that. So if we take the negative log of 2.3 times 10 to the minus 7th, we get 6.64. Now what's interesting is that is also the pOH, because our hydroxide concentration is the same as that. So essentially, the solution is still neutral. It's just at 50 degrees Celsius, water has a pH of 6.64 and it has a pOH of 6.64. The H plus and hydroxide concentrations are the same. You just have more of both of them. So that's an important distinction to remember, that although the pH of water decreases as the temperature goes up, the pOH also decreases because the value of Kw is increasing. So now we're going to take a look at what we're going to do with weak equilibrium problems. And we're focusing on acids for today. We'll throw in some bases soon enough. They work the same way, except that they're, opposites of acids. So keep in mind, strong acids, they ionize 100%. Weak acids do not. Their equilibrium constant is less than 1. That is what makes them, by definition, weak acids. So, with weak acids, you need to know what your major species present in solution are, and you should write balanced equations for reactions that can produce H pluses. Typically, there's only going to be one thing that's capable of producing H pluses in your solution. Using your values of Ka, decide which reaction will dominate and write the equilibrium expression. That would be the one with the largest Ka if you had a mixture of acids. You'll do an ice chart calculation uh, where we will assume that the change in concentration of the acid is approximately equal to 0 using our 5% rule, and then we'll calculate the H plus and the PO and the pH. Now I will walk you through a sample calculation at this point in time. So the pKa of hydrofluoric acid is 3 times 10 to the 14th. What is the pH of 0.027 molar hydrofluoric acid? So first of all, I need to point out what pKa is, because this is something that you will see fairly frequently. The pKa is the negative log of the Ka. So if you want to find the Ka, it's 10 to the negative 3.14. And so if we do 10 to the negative 3.14, that would give us a Ka of 7.2 times 10 to the minus fourth. Now, pKa's will become much more important when we start talking about buffer solutions, because essentially if you have if you're at maximum buffering solution, the pH of a hydrofluoric acid buffer would be 3.14. That's why this is a useful thing to know. If you're trying to make a buffer, you could look up pKa's. Also, it's an integer value as opposed to something in scientific notation. So it comes up frequently, but when we're doing calculations, we typically are going to need Ka's. So we have a solution of hydrofluoric acid. We're going to say that hydrofluoric acid is going to make H pluses and F minuses. Hydrofluoric acid is aqueous, as is H pluses and F minuses. Our Ka expression equals the concentrations of H plus times F minus over HA. Now keep in mind, you could, yes, theoretically put in the water over here as a liquid and write H plus as H3O plus. It doesn't affect our equilibrium expression, so we just ignore it. All right, I'm actually going to make a quick change to this problem. I'm going to change the molarity to be 0.35 molar hydrofluoric acid. So to solve this, we will set up an ice chart. Our HF concentration starts at 0.35. Our H plus and fluoride concentrations start at 0. This goes down by X, up by X, and up by X. And 0.35 minus X. So then we plug into our Ka expression. 7.2 times 10 to the minus fourth equals X times X over 0.35 minus X. And here we're going to assume that X is very small, so that 0.35 minus X is approximately 0.35. So then we take 0.35 times 7.2 times 10 to the minus fourth, and we take the square root of that, and we find that X equals 0.016 molar. And if we want to check the 5% rule, 0.016 divided by 0.35, that's 4.5%. So it's less than 5% of the 0.35 we were subtracting it from. So the 5% rule checks out for us. Now, this is not the answer. You have to be careful. I've not answered the question. This is our H plus concentration. The pH equals the negative log of 0.016, which is 1.8 0.80. So that's how we would solve a weak acid equilibrium problem. So, with that being said, what I'd like you to do today is try the second part of that worksheet that I'd originally shared with you on Friday, the section entitled Weak Acids, and see what you can do. Some of it is going from pKa's to Ka's. Just treat it like going from pH to H plus concentrations. And then I'm going to ask you to calculate the pH involving a weak acid, methanoic acid. So, with that being said, hope y'all have a great day.